Luckily, Moritz already told us about t-SNE, so I'll be able to make up some time with some of my slides. OK, so for me, data visualization is all about exposing patterns to the eye. And I'm always searching for ways to tap into deeper patterns. So patterns that feel kind of distinctly human, or patterns that we as humans can recognize but are really difficult to articulate to the computer. And I also love finding patterns that I just wasn't looking for in the first place. And this slide is for you, Lynn. Not much love, Al. So when we're exploring a new data set, we have a wide variety of tools, right? We have our summary statistics, we have our basic line and bar charts, histograms, scatter plots, all that, and this ever-expanding catalog of custom visualizations to draw inspiration from. But today I want to direct your attention to a relatively new set of tools that can change the way we explore large data sets. And these tools use machine learning to pull out patterns for us and give us new ways to navigate our data. And I'd like to demonstrate these techniques on my favorite data set, which is the Quickdraw data set. So if you haven't had a chance to play this game, the rules are really simple. The game asks you to draw a word, and you have 20 seconds to try to get the AI to guess what you drew. And if it guesses the right word, you get a point, and you do it again. So when the Google Creative Lab built Quickdraw, they had the foresight to save anonymized copies of the data of the drawings, and that kind of altered the course of my life forever. And so at this point, millions of people across the world have played this game, and Google has open sourced around 50 million drawings from those games. And this means we have on average more than 100,000 drawings for each of the 300 words that are in the game. So let's take a closer look at that data. And I think this data set makes for a great demonstration because it's fun, and the individual data points are so so relatable. And as a human, you can quickly identify with this representation of the data, like this cute cat. But also, it has several of the properties that you might expect from a more serious data set, right? So we have categorical data, like which word the drawing is of, or the country code of where it was drawn. We also have a couple of time-based dimensions. So we have the timestamp of when it was drawn, and the duration, like how long it took somebody to draw in seconds. And of course, we don't have who drew it because it's anonymous, but the real most important part of this data set, though, is the sequence of pen strokes that make up the drawing. And it's this list of points that carries the most meaning in the data set. It captures the way we as humans represent abstract concepts across the globe. But the thing is that sequences like this, which are common in a lot of data sets that we'd like to explore, are also the most difficult to dissect with traditional data visualization techniques. But just because something's hard doesn't mean we shouldn't do it, right? And since the data set was released, several amazing projects have applied all kinds of techniques to try to surface patterns and find interesting insights from this data. So one of these projects is by Jim Blenningham, sitting somewhere over here. And he made this awesome interactive project that explores questions around complexity and quality of drawings, right? So he uses proxies for complexity, like in this case, the stroke count in the drawings, that are they're straightforward to quantify. And you can get some pretty interesting observations out of that. Like if you just look at the distributions here for dog, cat, and horse, you see they're quite different. And as you kind of interactively play with this, you get to see how that manifests in the drawings. And he uses another proxy here for complexity, duration. And we can see from this that on average, it takes longer to draw a duck than a flamingo, which you might not expect. And also, on average, owls are always cute. But I want to note that the dimensions being visualized here are, they reduce the sequence of strokes to a single number. And these numbers do give us a manageable way to peek into the data, but they can't capture all of the features that are just by themselves. So I want to move to another project this great article in Quartz that deep dives into simple shapes. So for example, they go into circles and calculate whether, they developed an algorithm to figure out if the circle is drawn clockwise or counterclockwise. And we can see, for instance, that in Japan, people are much more likely to kind of start at the bottom and go clockwise, whereas in the United States, people start at the top and go counterclockwise. And they can then, they've extracted this feature of clockwise versus counterclockwise, and they can then visualize that, count up the percentages in different countries and look into these cultural patterns across the world. And this article does go deeper into why this might be, looking at things like writing systems or the way people are taught in school. But I want to point out that this feature was pulled out manually and took a pretty impressive amount of creative foresight to come up with. So on the next project, this team from IBM Research actually did a bunch of cool visualizations on the data. But the one I want to focus on is the use of visual averages to highlight patterns. And so a visual average works by layering thousands of lightly transparent drawings on top of each other until sort of a dominant pattern shows up. And this works especially well when we filter down to something like country codes where we can expect kind of regional or cultural differences to emerge. And so something like power outlets, which vary a lot region to region, you can see here pretty clearly that people represent them differently, depending on where they're from. And Kyle McDonald took this concept of visual averages to an extreme in this epic tweet storm, where he just shared a bunch of visualizations like this. So here, ice cream, right? Many countries believe ice cream cones have a single scoop of ice cream, and other countries believe there's 3 scoops, and I won't make a value judgment, but and he also makes excellent use of small multiples, of course, to visualize these across several categories. This one's really great. There's several countries in the pink boxes that I think mostly Asian countries seem to all agree that fish swim to the left. And then, there must be something in the water in Turkey because they know that fish swim to the right. I can see it right there. And the rest of the world, still is trying to figure it out. But it's a little, these are really great patterns that come out, but it's hard to dig deeper because a lot of the nuanced patterns get washed out by the average. And this becomes really apparent with a word like yoga, where I haven't even labeled the countries here because there's no real patterns to look at. When you average a bunch of drawings of yoga, it just kind of all blurs together like this. So what if we had a way to capture the nuance lost by averages, to automatically find interesting features in the sequence of strokes, as well as explore our data by more than one dimension at a time? Well, enter deep neural networks. And these aren't magic, although it sometimes feels like they are. But they have some amazing capabilities that, that we can leverage. And it turns out there's an open source network trained on the Quickdraw data set, and it's called SketchRNN. So it's learned how to draw the drawings by training on the Quickdraw data. And for example, on the left in this demo, a person can start drawing, and then the network will finish the drawings, different versions of the drawing on the right, so it's the purple strokes is the network drawing. And it's super fun to play with this and have a network that you can kind of come up with creative applications for a drawing machine. But for us as data visualizers, what's really exciting is the patterns that the network has had to learn to encode in order to generate these drawings. And so how do we get at these patterns? One way to do it is to ask the network how probable does it think a given drawing is. So if you say, is this a flamingo? It will say yes. These on the top are highly likely to be flamingos, and the ones on the bottom it thinks are probably not flamingos at all. And this is a really interesting lens to look through. This article has a lot of cool examples they pull out of flamingos that are really fun to look at and think about. But we're still reducing the data set to a single dimension to look across. And that's a problem because some of the most interesting representations, I think, of flamingos here are mixed in with the word flamingo, which clearly is not a flamingo. And we'd really like a broader view of the data. Because what if we want to see only badass flamingos, right? So yeah, we should just look at this for a little bit. So let me tell you just briefly how we can do that. And we'll go in a little bit of technical detail, but I try not to get too mathy. So SketchRNN belongs to a family of neural networks called autoencoders. And what's kind of important about autoencoders is that they find a way to compress data into a smaller representation that can then be used to generate new output. So here on the left, we have our drawing, and then we represented it in sort of the normal way as a sequence of x, y coordinates, as well as is the pen up or down, and that's kind of how the game works. And then we feed that data through this encoder neural network, which then spits out this list of numbers here, the encoded data. And I'm representing it as this squiggle. And then this network is actually made of two parts. So first it encodes the data, and then it can take any encoded data here. We can feed it through a decoder, and that gives us back stroke data, which gives us a similar drawing. This uses some probability, so these drawings are never exactly the same as the one before, but they're always pretty similar. And it's this squiggle here, this encoded data that is the key to our technique. And we call this a latent vector. And what we can do is we can extract the latent vector for any of our drawings. We can even get new drawings and get a latent vector for one of those. And this gives us a numerical representation of kind of how the neural network sees the data. And so, we just talked about how it creates these latent vectors by compressing data, right? It recognizes patterns. And so it makes sense that when we compare similar drawings to each other, right, these look similar to us, if we also compare their latent vectors, they'll also be pretty similar. And in our network, though, a latent vector is 128 numbers, right? This is sort of a sideways chart, but there's 128 numbers, and there's still kind of a lot to deal with in general. So we need a way to compare a lot of high-dimensional data points with each other. And thankfully, I saw Moritz's talk and learned about t-SNE. So here, each drawing in our data set, so this is all the faces that were open source, I think it's like 150,000 or so, is represented as a little translucent dot. And the t-SNE algorithm, right, puts similar drawings close to each other, so the bright spots are areas where there's kind of clusters of similar drawings. So we can zoom in on our map. It's not quite as fancy. We'll just go to the cluster. But the result is still fun. It's still a great grid. I'm a big fan. And as humans using our eyes, right, the pattern here is pretty clear, right? There's something going on with the shape of the eyes in all these drawings. They're all smiling. There's all circular heads. And if we go to a totally different cluster down here, we see a different pattern, right? And this one's kind of sad. Well, at least that's my interpretation of the pattern found here. But again, it's the eyes, right, the shape of the eyes and the lack of a smile. Yeah. And in this cluster, I think I've found the goofy dimension of our data. So let's get back to the idea of studying the complexity of our drawings, right? So if we use the word for cat, and instead of looking at the number of strokes or the duration directly, we can examine the complexity from the perspective of the neural network. So if we look at this cluster, we have one way to draw a simple cat, and all of these cats were drawn with one stroke. But then, if we look at this cluster, even though all these drawings use 3 strokes, I might argue that this is maybe a even more abstract representation of cat, right? Like universally recognizable by people. So what will we do with a few more strokes? Well, you might add a smiley face into your cat, or you might add some whiskers. But we don't need to stop there. We can have it all. And what I'm trying to show here is that we're not navigating by a single dimension right now. We're kind of going through a space that's much richer. So let's use that to revisit the problem of averaging, right? So let's look at our yoga drawings again. But this time, we'll see that the problem with averages is that they assume a normal distribution. They typically work best when you have a single mode in your data. And what we'll see with yoga is that there's several modes when representing in drawing form. And that starts with the different poses and the mat. It also includes the way people draw even a single pose. It's my favorite. I kind of put the best ones in the bottom right, so just, Also the way people give up on the game. But funnily enough, a lot of people actually got their point for yoga because the original classifier kind of still thought this looked like a yoga pose. Hey, you win some, you lose some. All right, so at this point, though, I do want to pause for a second, kind of step back a bit, and move away from our particular data set to make sure we're clear on a couple of things going on. And the first is that t-SNE is a general technique for visualizing high-dimensional data. It works on images, works on drawings, it works on all kinds of stuff. And really, it works on any data set that can be represented as a list of numbers, right? Like a vector is how we often describe that. But really, anything that's a list of numbers. But how well it works depends on how meaningful the representation is that you put into that list. So the second thing that I want to point out is that neural networks can also work on all kinds of data now, right? And when they work, they often create meaningful representations. Although they don't always mean what you think they mean, but there's something there. And in this figure is taken from Chris Ola's awesome blog article called Deep Learning for Human Beings. And in it, he has a neural network that's learned paragraph vectors to represent Wikipedia articles. And then he uses t-SNE to visualize those representations. And what comes out are clusters of topics. So we see things like a lot of sports over here, or films, or more specific things like asteroids. So these are labels kind of put on after the fact, right? Like the t-SNE has found these clusters and lets you find that. So I say all this just to point out that using neural networks to find better representations and then using t-SNE to visualize them is a generally good idea. And now back to the data set at hand. I want to talk about, so there's a term for the high-dimensional landscape that the neural network kind of creates with its internal representation, and that's called the latent space. And I love this term because the word latent is so mysterious, and space just kind of begs for exploration. So we can think of t-SNE as kind of helping us draw a map of this space, right? And just like a 2D map can never really fully and accurately represent our 3D globe, right? We always have distortion in our projections. A 2D t-SNE map won't be able to capture everything that's happening in high-dimensional space. But it can still be a really helpful way to navigate our space as we explore. And so here I've sampled a single drawing from each of the grid cells I was just showing. And then they're kind of darker if there's more drawings that they represent in that grid. And so if we zoom in a little bit, really fancy transition. In this part of the map, we see our sort of traditional smiley faces, right? This was just draw face, but we see a lot of smiley faces down here. We do see some variations in the shapes of the eyes or the mouth. More richer eyes going on over here, no mouth going on over here. So there's a lot of fun stuff to find here. And then if we kind of pan to the left and up, we get all kinds of clusters. So we see faces with long hair going on over here. We got short hair and ears. There's some curly hair somewhere in here. There's even faces that have no tops to their heads. It's like a style. And now we can kind of bring it back to the idea of, remember the averaging the country code. So if we're looking at power outlets and how people represent those across the world, instead of averaging, we can also filter this view. So if we say, all right, here's our map, only showing power outlets drawn in Japan. When we zoom in on that, we see kind of the standard, this is called like a type A, I had to Google this, type A outlet, which is these two vertical lines, right? Often in sets of two, like this, and it's very common in Japan. But unlike when you average, when you do this, we pan to another area, we find these really awesome, interpretations of power outlet. Maybe they were thinking power lifting, I'm not sure. But it's these kind of delightful moments that you get when you get to really dig into the data. And I also want to bring us back to complexity for a second. So here's all of our cats. And this is great. So if we take all our cats and then we filter them down to just the cats drawn with a single stroke, it's actually much less interesting, right? We see sort of the profile view that I showed you as one of the clusters earlier on, but there's not much else going on. However, if we take a look at octopuses, I also had to Google that. It's either octopodes, but it's not octopi. Anyway, there's a whole bunch of octopus. Data is plural. These are all drawn with a single stroke. And you see they're all over the map, right? So just being a single stroke doesn't limit the expressiveness of drawing an octopus. And you might even be able to imagine, right, like how you would draw an octopus in one go. But then if we look at the view for, wait, no, this was a single stroke, sorry. If here we're looking at all the octopuses that are more than 14 or more strokes, right? So they're not quite as widespread. But there's still some quite complex examples of octopus going on. And my favorite cluster is this one. There's no scientific basis for this slide. It's just awesome. So, I'd like to close by noting that the different ways in which people draw are kind of like different notes in some universally human scale. And the clusters we've explored are the result of thousands of strangers harmonizing together. And so with that, I'd like to close my talk with the sound of a single ohm. Just kidding. Namaste. Thank you. So, since we're in France and I'm a couple minutes early, can I have 2 minutes to do a little encore? Is that okay? Yeah, because I prepared a few more views of the data just because I love it so much. Here's our map of dogs, and here is my favorite dog cluster. Here is a map of tigers, which you might expect to be pretty similar to cats, and often are. And here are my favorite tigers. It's really cool. Here's a map of penguins. Everyone loves penguins. There's movies about them. And these are some nice ones. These are frogs. A little harder to draw a frog, I think, right? If I asked you to draw a frog, what would you do? Something like this? This little guy, right? I think this is the most professional in this set. The thing is, right, you have 20 seconds to draw, but also if the game guesses correctly, you're done. So they didn't get to draw their eyes with, they're like, that's a frog. finally, we have pigs. And that's all, folks. Thank you.